Hello everyone, this is Rahul. Welcome to my video lectures on computer organization. In this lecture, we are going to deal with signed numbers. Generally, computers need to perform calculations and operations on both positive as well as negative numbers. Till now, we have seen only positive numbers, but we haven't seen any negative numbers. So the computer has to know how to differentiate between a positive number and a negative number. Generally, talking about positive and negative numbers, we represent positive numbers with a sign such as plus 25 represents a positive number and minus 25 represents a negative number. In the similar manner, we can obviously say that if we introduce a special bit to represent a positive or negative number in a binary number, such as if we have a number 3 in 3-bit representation 0 1 1, we introduce a special bit 1 to represent it in negative number. This one is sign bit and this is magnitude. This number represents minus 3, and if you want to represent a positive 3, in place of 1 we write a 0 0 0 1 1, and this bit to the left is a sign bit, and this thing after the sign bit is magnitude, and hence the name sign and magnitude representation. Sign and magnitude, because we have both sign and magnitude in this representation. But there is a problem with this representation. Hardware designers found it very difficult to represent in this format. So they came up with a special and alternative way called as 1's complement number system to represent signed numbers. 1's complement. This is a better alternative than sign and magnitude numbers. In 1's complement numbers, suppose we have a 4 bit binary number, then how do we represent both positive and negative numbers? For 2, we can represent it in 4-bit binary number as 0 0 1 0. 3, we can represent it as 0 0 1 1. 5 as 0 1 0 1. This is similar to what we have seen earlier. The positive numbers never change in any representation, they remain the same, but this 0 represents a positive number. Now let us see the corresponding negative number of these numbers. Minus 2 can be represented in 1's complement just by interchanging the zeros to 1's and 1's to zeros. Flip the values, that is 0 becomes 1, this 0 becomes 1, this 1 becomes 0, and this 0 becomes a 1. To represent minus 3, this 0 changes to 1, this 0 changes to 1, this 1 changes to 0, this one changes to 0. For 5, this 0 as 1 0 1 0. Let's look at here. For the positive numbers, we have a 0 in the MSB position. This is MSB, most significant bit, and this is LSB, least significant bit. Whereas in the negative numbers, we have a 1 in the most significant bit, which differentiates between positive and negative numbers very easily. Now let us see what is the range of values a 1's complement number can represent. Let us consider this 4-bit binary number. What is the maximum value of a positive number represented by a 1's complement? The MSB, that is the starting bit, must be 0 always for the positive numbers. Now the remaining bits are 3 bits. For a 4-bit binary number, if we take the first bit as 0, then the remaining bits are 3. So we can, this is the maximum positive value that can be represented in 1's complement, and this value is 7. The next, this is 7, and the next least value is 0, 1, 1, 0, that is 6. And the next value is 0, 1, 0, 1, which is 5. The next value is 0, 1, 0, 0, which is 4. 0, 0, 1, 1, which is 3. 0, 0, 1, 0, which is 2. 0, 0, 0, 1, which is 1, and 0, 0, 0, 0 is 0. All these are positive values that can be represented in 1's complement. Now let us represent the negative numbers. We can represent the negative numbers by interchanging the zeros and ones. For 0, interchange the zeros into ones. 1, 1, 1, 1, which is negative 0. All zeros, if you have all zeros in 1's complement, then it is positive 0. If you have all ones, then it is negative 0. Similarly, we can flip the ones to zeros and zeros to ones for positive ones, and we get the result as 1, 1, 1, 0, which is negative 1. For positive 2, the corresponding negative 2 is 1, 1, 0, 1. This is negative 2. And negative 3 as 1, 1, 0, 0. This is negative 3. And 1, 0, 1, 1. This is negative 4. And negative 5 is 1, 0, 1, 0. This is negative 5. Negative 6 as 1, 0, 0, 1, minus 6, and 1, 0, 0, 0. This is negative 7. So these are all negative numbers. Negative numbers that 1's complement number system can represent. In the previous video, we have seen that an n-bit binary number can represent what range of values? It can represent 0 to 2 power n minus 1. For 4-bit numbers, it represents 0 to 15 values. All the values between the range 0 to 15 are represented by n-bit binary number. But n-bit binary number in 1's complement represents the range from some positive value, from some negative value to some positive value. So the range of 1's complement number, 1's complement So the range in 1's complement number is, before that let us observe some few things. 4-bit binary number represents 16 values, that is 0 to 15, but here the positive values are from positive 0 to positive 7 and negative values are from negative 0 to negative 7. So we have divided into half. The 4-bit the range that this can represent is divided into two halves. So positive numbers are 2 power n by 2 numbers. Negative numbers are 2 power n by 2 numbers, that is 2 power n minus 1 positive numbers and 2 power n minus 1 negative numbers. So the range that a 1's complement number can represent is from minus 2 power n minus 1 minus 1 to positive 2 power n minus 1 minus 1. This is the range of positive and negative negative numbers are represented in 1's complement system. If we substitute n as 4, we can get minus 2 power 3 minus 1 to plus 2 power 3 minus 1, that is minus 7 to plus 7. This is the range 1's complement numbers are represented in. Next we will look at another alternative. We need another alternative because we have a problem here. We have two zeros, a positive 0 and a negative 0. There is an alternative that eliminates this problem, which is popularly known as 2's complement number system. 2's complement number system to represent signed numbers. 2's complement. 2's complement signed representation. This is used in almost all the computers today. In 2's complement numbers, positive numbers are represented. Let us assume a 4-bit binary number again. Then a positive 3 is represented as 0, 0, 1, 1. To get the negative number, all we have to do is we must perform the 1's complement first. How do we perform 1's complement? We flip all zeros to 1's and 1's to zeros. So we get 1, 1, 0, 0, and then we add a 1 at the LSB. So we get 1, 1, 0, 1. If we have positive 4, 0, 1, 0, 0, we can get 2's complement negative 4 as performing 1's complement first, that is 1, 0, 1, 1, and adding a 1 at the LSB, that is 0, 1, 0, 1, 1, 1. The addition is, I have performed the addition as follows. The general addition for binary numbers is 0 plus 0 equals 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 equals 0, and carry a 1 to the next bit position towards the left. Okay, this is the addition. So we have represented in 2's complement. There is another way by which we can represent 2's complement. We can convert a positive into negative. We have positive 4 as 0, 1, 0, 0. Now we get the negative 4 as, start scanning from the right hand side, that is from LSB. If you encounter a 0, write the 0 as it is. You encounter a next 0, write it as it is until you get a 1. write it as it is. From the first one onwards, flip all the zeros to ones and all the ones to zeros. Now flip this 0 to 1. See, we have got the same number back. Now let us perform for this number. Say we have a number 1 0 1 0 1 0 0. Now we have to find the negative number corresponding to this positive number. So scan from the right side, that is 0, write as it is, 0, write as it is. We have encountered the first one, 1 and 0, flip it. This one, flip it. This 0, flip it. This one, flip it. This is a positive number, and this is a negative number, and this is a positive number corresponding to this negative number, because we have a 1 in the MSB. If you have a 1 in the MSB, then it is always a negative number in 2's complement representation. If you have a 0 in the MSB position, then it is a positive number in 2's complement representation. For 2's complement representation, let us see what is the range of numbers that it can represent. Let us start by writing the highest positive value, that is 0 followed by all ones, as we have seen earlier. This represents positive 7, positive 6, positive 5, and 0 1 0 0, positive 4, 0 1 0, 0 0 1 1, positive 3, 0 0 1 0, positive 2, 0 0 0 1 as positive 1, 0 0 0 0 as positive 0. Now we have represented all the positive numbers. So let's start writing the negative numbers. For the 0, the corresponding negative value is, start from this LSB, write the 0 as it is, 0 0 0. We haven't encountered any 1, so the 0, this is negative 0. You can observe here that the positive 0 and negative 0 both are equal. We don't have different values for positive and negative zeros. This is same. This has eliminated our earlier problem of 2 zeros. Next we convert this 1 into minus 1 as the procedure that I have explained before. We have encountered a 1, first one. We haven't encountered any zeros. So write this one as it is and flip the next values. That is 0 changes to 1, 1, 1. This is positive 1. For this positive 2, the corresponding negative 2 is, write the 0 as it is. We have encountered the first one, and this is 1 and 1. This is negative 2. And for positive 3, we have encountered the first one. The next one turns to 0, 1, 1. This is negative 3. And for positive 4, 0, write the 0 as it is. Write the first one as it is. The next 0 becomes 1. This is negative 4. And for the 5, write the first one as it is, the next 0 as 1, the next one as 0, the next 0 as 1. This is negative 5, and negative 6 is 0, 1, 0, 1. This is negative 6, and are we writing it right? 0, 1, 0, 1, okay, right? And 1, 0, 0, 1. This is negative 7. Alright, we have represented all the positive values and all the negative values. But we can see here that A 4-bit binary number can represent what values? A 4-bit binary number can represent 16 values. Let us check, did we get all the 16 values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. One value is missing, and that is 1, 0, 0, 0, which is -8. We get this extra number because we have eliminated an extra 0. That is a positive. We have only one 0 positive. We don't have positive 0 or negative 0 in 2's complement number system. We have successfully eliminated this. Now let us see the range of values that 2's complement system can represent. We have 8 negative numbers, so the negative number range starts from 8 minus 2 power n minus 1. So the negative range is -8. 2 power n minus 1 is 2 power 4 minus 1, that is minus 2 power 3 is -8, to the positive value, that is 7, that is 2 power n minus 1 minus 1. This is the positive value. This is the range of 2's complement values, minus 2 power n minus 1 to positive 2 power n minus 1. Now let us summarize what we have seen today. We have seen the ranges of the signed numbers. In sign and magnitude, the range is minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. And for 1's complement, the range is minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. And for 2's complement representation, 2's complement, the range is minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. We can observe here that these two are symmetric ranges, which means both positive and negative numbers are equal, whereas this is asymmetric range. Positive values and negative values, the range of positive and negative values is different. So this is the observation that we have to keep in mind. Oh yeah, I forgot to mention one point, that is, consider a number, any number in signed representation number. We take example, we take 4, positive 4 as 0, 0, 0, 1, 0, 0. Now if we extend this sign bit, this is a sign bit, right? If we extend the sign bit towards the left any number of times, then the value doesn't change. That is, positive 4 is 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0. Any number of zeros towards the left doesn't make any sense. This is the same value as this. Now consider the negative 4. Negative 4, we get negative 4 as, scan from the right, 0, 0, 1, 1. This is negative 4. If we extend the sign bit towards the left any number of positions, such as 1 1 1 0 0. This is a negative 4. If we extend this 1 1 1 1 0 0, this is also negative 4. If we extend any number of times, then the value remains the same. We can convert this negative 4 back into positive 4 to recheck whether it is same or not. We will convert this binary number by performing 2's complement again. If we perform a 2's complement on a positive number, we get a negative number. If we perform a 2's complement on a negative number, we get back the positive number. Similarly, it goes the same with 1's complement. So this number, we scan from the right, 0 0 1, and from the next bit we flip. Hey, this is same as positive 4. So extending sign bit any number of times to the left doesn't change the number. So that's all for this video, guys. I hope you find the video useful. So please like the video, share it, and subscribe to my channel. Until then, happy learning.